Hey ladies, this is Miss Bathker, and today we're going to look at the bisectors that are at work in triangles. It's kind of cool that bisectors and triangles have some very unique properties, and we're going to examine those today. So first, let's look at a sample problem here that sort of reviews the concept of a bisector. Remember, to bisect literally means to cut into two. And so here we're given a scenario where we have an angle STU. And I don't really know anything about that angle. It's not indicated whether it's obtuse or right or acute. So I'm going to draw it as an obtuse angle just to facilitate or visualizing it. But keep in mind that just because I'm drawing it this way doesn't mean that that is the physical reality. We might actually find that angle STU is a smaller angle. This is just for demonstration purposes. So here we have angle STU, and I'm told that ray TM bisects that angle, or cuts it into two. So I've already established point T up here. TM must go straight through the center of that angle in such a way that it creates two equal halves of the angle adjacent to each other. Now that I have that diagram down, let's look at what we're told about the two angles. First, we're just told about angle STM, that it equals 5x plus 4. So I'll fill that in right here. We're also told that angle MTU equals 6x minus 2. So we have these two algebraic expressions for the halves of this angle, and we're asked first to find the value of x. Since we know that these two angles are congruent to each other, I can simply set 5x plus 4 equal to 6x minus 2. And when I do a little bit of algebra there, I find that x equals 6. In the second part of the question, I'm asked to find the measure of angle STU, which is neither of those smaller halves, but it's actually the larger angle, STU, the original angle that we started with. Since I know that x is 6, all I really have to do is plug in that value for 5x plus 4 and 6x minus 2, and then add those smaller angles together to find the overall value of or measure of the larger angle. So I'll do that. I'll take 5x plus 4, plugging in 6 for x, and add the value of the other angle, 6x minus 2. So when I do some arithmetic there, I'll simplify first using PEMDAS. I get 30 plus 4 plus 36 minus 2. And of course we go now from left to right, so we get 34 plus 36 is 70, minus 2 is 68. So we mentioned before that just because I happen to draw angle STU as being an obtuse angle, it doesn't necessarily mean that that's what it is. I was just drawing it so that we could visualize the angle. And in fact, now we've found that really it really wasn't an obtuse angle, it was an acute 68-degree angle. But we were able to figure all of this out because we knew the meaning of the term bisect. To bisect is to cut into two. And you don't just necessarily bisect angles, sometimes you can bisect line segments, as we'll see in the next theorem. So as you can see in the definition here, we see that the theorem tells us if there is a point on the perpendicular bisector of a segment. Well, let's look at what that means first. So let's say that we have a line segment. I'll call that line segment XY. And I'll draw a perpendicular bisector of this line segment now. So first I notice the term bisector. That means that this line has to cut the original line segment in half, into two equal parts. And it also has to be perpendicular to the original line segment. So this is a perpendicular bisector, and I'll call this line segment MN. So in this example, Since line segment MN cuts line segment XY into two equal halves, and it's perpendicular to line segment XY, we call line segment MN the perpendicular bisector of line segment XY. The second part of the perpendicular bisector theorem tells us that if we have this perpendicular bisector and we have a point lying somewhere on that bisector, let's say this point right here, then that point is equidistant from the endpoints of the original segment. The endpoints of the original segment, of course, were just x and y. So this point here, I'll call this point N, or excuse me, point P. This point here must be equidistant from the two original points. That is, Px must be equal to Py. Let's look at an example of this. In this diagram here, we see that line segment CD is the perpendicular bisector of line segment AB. I know that because it clearly cuts AB into two equal halves. We see that with the tick marks, and it's perpendicular to line segment AB. Because of that, I can conclude that point C here is equidistant from point A and point B. So CB must be equal to CA. CA equals 5. This same theorem also holds true for point D, since it's another point that lies on the perpendicular bisector. If D lies 6 units away from point A, then it also lies 6 units away from point B. And I can conclude from that that DB has a value of 6 units. There's an interesting corollary to the perpendicular bisector theorem, and that's called the angle bisector theorem. This tells us that if the point is on the bisector of an angle, that is, the ray that cuts an angle in half, then that point is equidistant from both sides of the angle. So, for example, if we have an angle here, I'll call this angle X, Y, Z. And I draw a ray inside there. I'll say that it has point P on the ray. And I establish that line segment YP is an angle bisector. That means that it cuts angle XYZ into two equal halves. So angle XYP has the same measure as angle XYP, excuse me, ZYP. XYP has the same measure as angle ZYP. Now if I put another point along this line, anywhere along here, it could be farther down than angle P, or it could be closer to the vertex. This point is equidistant from the sides of the angle. So if I connect it here via a straight line, what I've established are two perpendicular and congruent line segments. Let's look at an example. In this diagram here, I can immediately conclude that line segment CF is the angle bisector of the larger angle ACE. And I know that because I'm given these marks here, making those two angles congruent. Because of that, because the fact that F lies on that angle bisector, I can conclude that BF is equal to DF. They have the same length. Now in this case I have to do a little bit of algebra, because I'm given BF only in algebraic terms. I'm given BF is equal to 5x, so I'll substitute that in, and I'm told that DF equals 2x plus 24. Now we can do a little bit of algebra there. And you conclude that x has a value of 8. Since I'm asked for the value of the length of FD, I want to plug that value of x into the known value of FD, which is 2x plus 24. So 2 times 8 plus 24 equals 40. And the correct answer to this question is D. Down below here, we'll actually use what's called the converse of the angle bisector theorem. This is essentially working backwards. Okay? If we know that we have a point K in this diagram that is equidistant from both sides of the angle, we know that because we have the 2 tick marks here. One side is 10 and the other side is also 10. Then we know that K is an angle bisector. And we know that angle DEK must be congruent to angle HEK. These two angles must be the same size because K must lie on that angle bisector. So let's look at what we're asked about this diagram. The first question is, according to the diagram, how far is K from ray EH? Well, that's a fairly straightforward question. We're actually given that value. K has a distance of 10 newtons from ray EH. That's given to us right here. From ED, it has the same value, it's the same distance, since we know that K is the angle bisector and the tick marks are indicated there. For part C, we're asked for the value of x, and now we need to use this relationship here that we've established for the angles. We know that angle DEK, which is given as 2x, is congruent to angle HEK, which is given as x plus 20. If we do a little bit of algebra there, we can conclude that x equals 20. And finally, for part D, we're asked for the value of angle DEH, the measure of angle DEH. Since half of that angle was 2x, I know that twice 2x will give me the full value of that angle, and that'll be 80 degrees.